Welcome to the third annual conference of architecture and civil engineering. This has become a very interesting conference over the past 3 years, and it's been very interesting to be a part of it and to get to see how it's grown. Its reputation has been growing around the world, and there are getting to be more and more interesting participants. I'd like to just begin by thanking Dr. Anton Ravindran, who is the organizer of GSTF. So welcome to all of you presenters and participants and the other keynote speakers. I've wanted to open my remarks each time as I've spoken here just thinking about what are the big challenges that are confronting us in the architecture, civil engineering, and construction industries. And these are issues that are really pressing for change and for innovation and for a kind of renewed creativity in all of these fields. So throughout the world, and particularly in Asia, rapid urbanization is a very pressing issue. At the same time, our building systems are becoming increasingly complex. The range of materials that we work with are increasingly rich, but difficult to understand without a great deal of expertise. We're also in a period when construction is especially expensive all over the world, and when affordability is a very important issue for all of us. And then finally, probably most importantly, we're at a point in the world where sustainability is a very critical issue for human inhabitation of the Earth. And we've known about this for a long time, but the pressures are increasing, and it's also increasingly clear to us that construction plays a major role in the way that the world can be a sustainable place. So all of the streams of papers that are going to be presented here will include a number of different approaches and ideas about all of these issues, and this becomes a kind of umbrella background for this discussion that we can have among us here today. So as we are starting to deal with increasingly pressured issues of construction, and as the technology that we deal with becomes increasingly complex, the importance of collaboration between architecture and engineering is, between architecture, engineering, and construction professionals becomes increasingly difficult and increasingly important at the same time, because none of us can just work independently any longer on the complex systems that we deal with. So I've been very interested in drawing as a means of communication between these various fields, and drawing plays a major impact in the way that we all can share and collaborate. So that also shares or provides a kind of background for some of the issues that we've been talking about here. As we start to deal with these more complex issues of interdisciplinary collaboration and increasingly complicated technologies, it also becomes increasingly apparent to many of us, especially of us who are teachers and also practitioners, it becomes increasingly apparent that we not only need to become better at some of the technological means of collaborating, but we also have to start becoming more practical again, because we've had a period, especially in the digital flowering of potential in design, in analytics, in construction processes, in which we've started to harness the power of computing, the power of high technology to accomplish things. But in doing these things, we've started to specialize more in drawing, specialize more in some of the issues of projecting information and projecting processes. And we started to lose touch somewhat with the practical issues of construction. This becomes especially apparent to many of us who are teaching young and emerging architects and engineers. It becomes increasingly apparent that many people entering the professions today have far less experience in construction and in just the simple, practical making of things in the world than many of us had in earlier generations. So students are, it's been kind of surprising to me over the past 10 years, for example, to see how students become more and more distant from the practical realities of construction. And that doesn't even just mean building construction, but just basic relationship to tools, basic relationships to the physical aspects of the world becomes a more distant issue. So as educators and as professionals, it becomes important nowadays not to any longer assume that people entering our professions will have worked with their fathers, worked with their families, their grandparents in building. There's far less of an assumption that people know something about what materials feel like, what is the weight of materials, what are the effects of gravity, all of these things that are a part of what we sometimes think are just a kind of natural learning process for young people. And now, even though students entering design courses in architecture and engineering, even though they have tremendous skills in visualization, in digital technologies, we have to sometimes assume that we need to go back and deal with the relationship of these new technologies to the physical facts of construction and physical experience. So I'm going to look a little bit at drawing as a background for some of the work that we've been doing with students, but relating the drawing of things to the construction of things. And so what I'd like to do is show a few examples of projects that my brother Peter Anderson and I have worked on with students over the past few years, in which we've tried to start with imaginative drawing and technologically advanced resources of drawing visualization, analytical tools and fabrication, digital fabrication tools, and then trying to get these to move forward into physical constructions that allow the students to become very much aware of how their drawings and their projections actually start to interact with the physical world. So I'm going to start with a project that Peter has been working on for a couple of years at the California College of the Arts in San Francisco. This is a project that's a lightweight classroom project for a small island area off the shore of Guinea-Bissau in Africa. It's an area that requires very lightweight sorts of construction materials because it's in very shallow water. You can't bring any large ships out to these islands. So everything has to be carried in. So all of the materials have to be carried into the islands and assembled with minimal tools in these Bijagos Islands. So the project for the students was to conceive of a very lightweight structure with simple materials that could be hand carried from offshore boats onto the land and then quickly snapped together with minimal tools and minimal labor. So this has been a project under prototype for several years, and it's had quite a few iterations looking at the educational possibilities, the furnishings for these rooms. There's been a lot of interaction with some foundations in Lisbon and in Guinea-Bissau who are supporting this research. So it's very practical, it's drawing-based, but then the ambition is to build this thing. So there are drawings dealing with the CNC cutting of the materials that are then quite technically advanced in terms of some of the tools, but all of this is being directed towards a simplicity of construction on the site itself. So the students are learning, first of all, how to project the possibility for these buildings. Then they send their drawings to the CNC router. They cut all of these pieces, and then they start to snap them together. And of course, in doing that, they are encountering many of the kind of physical construction issues that we all deal with in terms of getting teams of people together, getting the right tools and materials in the right place at the right time, trying to lift assemblies up into place. There's a whole world of practical engagement with construction processes that are never imagined by students ahead of time. And this sort of relationship between construction process as it actually unfolds and our imagination about building and our ways of drawing are something that become something that's very eye-opening for students. And it's quite gratifying to see how the kind of initial thought that this is hard work, it's a lot of drudgery, there's a lot of difficulty. It starts to, once the construction is underway and completed, there's a sort of joy and sense of accomplishment and mastery that is never quite so intense when the final product is just a drawing or a projected building. So this is another project, a very quick, simple one that we worked on at the University of Oregon with a group of students. Here again, there was an ambition to take a very simple set of materials and to create, in this case, it was a space at the university as a place for smoking outside of the buildings as it's become increasingly difficult for people to smoke cigarettes inside buildings in the United States and around the world. There's become an interest in having this sort of outside student space for smoking. So this wasn't something we especially wanted to encourage, but this was what the students thought would be a good thing for their school. So they built this project called the Burn Box, and it dealt with some very ancient traditions of finishes, charred finishes that are typical in traditional Japanese construction and in traditional Scandinavian and Northern European construction, where all of the wood timbers are burned as a preservative method. And in this case, there were some digital drawings that informed these that informed the forms. Then this was all built as physical models to test the production of this small building as a kind of stacked set of material components. Then the students started to build this on site. They worked with the foundations, the basic structure, building the components, preserving the components with fire and getting each of the pieces ready, pre-drilled and ready for assembly. So again, it's a teamwork project with lots of sub-assemblies that require a quick production of each element, getting ready for the next team to produce the final project. So again, there's kind of a transformation in the students' experience between what they've drawn, what they thought was going to be the process of construction, and then the actual production of the product on site. So there's also a few more technologically advanced projects that our students have worked on. So this is a project that Peter did with his students at the California College of the Arts and with an engineering school in San Francisco. It was for the Solar Decathlon, which is an international competition for net zero energy housing, sponsored by the United States federal government. So in this case, 10 schools from around the world design and produce a off-site manufactured building, so something built by the students and brought to a competition site in Washington, D.C. in the United States. So the students, again, went through a design competition process. They had a design chosen, then they worked through a design development process. There was a lot of engineering of the mechanical systems, the photovoltaic energy systems, the ventilation systems, lots of construction detailing. And again, all of these parts of the project, as we often know, take a tremendous amount of design time. And we sometimes think that now the project is finished and the decisions are made. But then once the students started to build the project, of course, all of the decisions are revisited. Many of the design ideas are understood to not really be feasible, and they have to work through the problems on the site and construct the project. So in this case, the building was built as components in California, then shipped across the country and put together by the students. So it was built by the students in California, brought across the country, and then set up on the National Mall in Washington, D.C., where I guess there are maybe more than 10 different schools here competing. So in each of these cases, universities from around the world had teams of architects, and various building science people who were trying to make the most energy efficient building and the most kind of sound design strategy for a small single-family off-grid building. In this case, Peter's team won the first prize in architecture and the third prize in the mechanical engineering of the photovoltaic system. But here again is a kind of complex ambition that is a design process, a drawing process, a collaboration between architects and engineers, and then the ultimate educational aspect of it really starts to come together in the physical construction process. And so I'll just quickly show two very different projects, and then I want to wrap up with a very recent project in Japan with my students. So this is a project for emergency housing as a prototype for emergency housing for natural disasters around the world. And in this case, the students used as examples the earthquake in Kashmir from a few years ago, the tsunami in Sri Lanka, and a potential earthquake in the United States, and attempted to come up with a building system that would be a kind of universal prefabricated disaster relief structure. So in this case, they did a lot of modeling, a lot of physical modeling, a lot of large-scale prototypes, and they were trying to make something that had fairly complex parameters, something that could quickly fold up and be transported very compactly, something that could be quite affordable, so they used bamboo as a primary structural element. And they, based on their study of these disasters, they recognized that one of the major issues is not just the immediate aftermath of the emergency and the need for housing, but there's a kind of ongoing need that usually continues for many weeks and sometimes months, in which people have to actually inhabit these emergency structures and provide an adequate means of living over time and through multiple seasonal changes. So this was intended to be a very adaptable structure and something that would have insulation, it would have water catchment capabilities, it would have internal ventilation, and it would even have water filtration and waste resource filtration built into it. So it's a fairly complicated structure, multiple layers of fabric skins to allow for flexibility in a variety of different climates and situations. And here again, there were fairly complicated drawings and analytical tools involved in the initial design process, but the actual construction was the kind of highlight of the project and became a very important part of what the students were learning here. So one other related example was a kind of simpler project, but one in which we wanted to model a complex construction process with multiple teams that would work on what would be essentially a non-normal sort of construction project, so that the students wouldn't be able to always revert to standard construction details that they might find in books, but instead would have to solve every construction detail as a new issue. So this is a solar hot water heated outdoor mini amphitheater for watching films outside in San Francisco. And the idea of this was to use solar heating during the day when it's very sunny to produce heat in this kind of soft furniture infrastructure. To collect that heat, use solar powered pumps to pump the heat into water bladders in the in this large furnishing, and then to re-radiate that at night so that when it becomes cold, as it does in San Francisco in the evening, they would have a place to enjoy the warmth in the cold air. So this was a fairly complicated little structure. It had a structural team, it had a plumbing team, it had an electrical team, it had an exterior skin team, and then it had an interior mechanical system team. So there's quite a range of drawing that had to be integrated by different teams. The simple structure all had to be integrated as one coherent system, and then the students had to source all of the materials, build the system as components, and then come together in a one-day, very quick construction process and put all of these assemblies together into one piece. So I'd just like to finish with a project that was just finished in construction. This is a group of my students from the University of California that entered a competition in Japan to build a community structure in a small village in Hokkaido. And there were, again, about 20 schools, I think, around the world that were invited to compete on this. The first project, of course, is to design a vision, and in this case, the idea was to build a kind of community living space that celebrates the seasons and celebrates the cycles of harvest in this area. So the students won the competition and then had to figure out how to build this thing. And it's this is one of the real highlights of getting to work with a team of students like this, to first work with them on the drawings, and then to work with them once they realize they're going to have to build this on detailing it. So it's quite a remarkable building. The students worked on this first at the University of California, then during the construction process, they spent the summer in Kengo Kuma's office in Tokyo doing a detailing phase of the project, working with engineers and construction people there. And then they built this working with with professional carpenters, but working closely with them on the island of Hokkaido. So they built this very sort of complex wood structure. It's wood above the ground, and then the ground itself has a rammed earth structure that creates the groundscape. So they built the construction drawings. They built a number of presentation drawings that showed how this related to the climate, to the cycles of nature, the cycles of planting. So there was a lot of visualization of the natural cycles of life in this place. Some very detailed drawings, but again, the lesson here is that the drawings are part of the ambition, and then there's the shock of construction and all of the issues that go along with that. So first detailing it, working with carpenters, some of the master craftspeople of Hokkaido who worked on this, and bringing some very modern materials, some very traditional construction techniques to build this structure that was a place out in the fields of this village where in each season of the year they could celebrate the harvest, celebrate the various foods and traditions, and be kind of the earth or up in the sky with the fruits of their labor in the village. And the actual construction actually ends up looking very much like the drawings, which is not always the case. So this was quite a remarkable achievement for these students. So just to finalize, the most important thing that I think that we can all imagine as architects, as engineers, as construction people, and as teachers of people emerging into this profession, we have to imagine a world in which we not only draw, we not only solve technological issues, we not only do deep research in certain technical problems, but we also need to imagine that we are actually interacting with the world, and we have to be ambitious and practical and very physical in our engagement with it. So welcome, and I look forward to hearing all of your ideas as well. Thank you.